We now take a look at yet another application of linear systems. I think, I hope by now you've gotten the sense of how diverse this set of applications is, right? And we're going to look at one that now involves balancing chemical equations. So the assumption that I'll make is that you are familiar with the concept of a chemical equation, and maybe you even have some techniques from chemistry that you remember how to balance them. And what I'm about to present, I'm not saying that this is like the now way that you should always do it. It's just I'm saying here is one possible way to balance a chemical equation, and it just happens to relate to this topic of linear systems, right? So what I'll do, I'll just do an example and kind of walk through the process. Now, how do we convert it into a linear system? And then we will actually solve this particular one, right? So I'm going to write down a chemical equation, and it is so Al3 for aluminum, and then we have CuO, so copper oxide, and then it produces, in the presence of heat, aluminum oxide, I think a dioxide, and then copper, right? So plus Cu, right? So that's an example of a chemical equation. And for it to be balanced, the goal is to find coefficients for each of these molecules. So we need to find x1, x2, x3, and x4 such that we have the same number of atoms of each element on both sides of the chemical equation. And I'm looking at something here. This needs to be a 3. So let's make that a 3. There we go. All right. So the goal is to find, so what is our goal? Find whole numbers, right? So find x1, x2, x3, and x4, whole numbers, in other words, positive integers, right, to balance this equation. And the thing about this is, I'm not going to state it in this context, but the same principle that guided us to being able to solve general networks also applies here. It's another idea of conservation of matter, right? We're not creating or destroying any of these elements. They're just being transformed from one form to the next, right? So that's the sense of balance that we're looking for in this equation. So there are 3 elements present. We have aluminum, we have copper, we have oxygen. So for each of those, for this equation to be balanced, again, we have to have the same number of Al on both sides. We have to have the same number of Cu on both sides. We have to have the same number of O on both sides. So let's do it element by element. So let's start with Al, aluminum. Well, on this side, right, because of that subscript 3, we have 3 times x1 of the ALs, right? So we have 3 times x1 here. There is no AL here, so it's like 0, right? And then on this side now, so the right arrow is really your equal sign, right? So 3x1 of the ALs on the left, and then on the right we have 2x3s. So we put a 2x3 there, and that's it, right? So whatever we come up with for x1, 3 times that number is going to be equal to 2 times whatever we come up with for x3, right? And we do this for each of the elements present. So the next one is copper. So on the left, we have only 1 times x2 atoms of copper. So it's just x2, again, is equal to, now over here, again, we have just 1 times x4 atoms of copper. So there, right? So whatever we come up with for x2, it has to be equal to whatever we come up with for x4, right? And then we have one more element, oxygen, so O. So on this side, we have 1 times x2 atoms of oxygen, so x2 there. And then what do we have on the right? Well, for O, we have 3 times x3, right? So 3 times x3. So now let me write this system in the more standard way. So let's move all our variables to one side. So we will have 3x1 minus 2x3 is equal to 0. Then we will have x2 minus x4, that's equal to 0. And then x2 minus 3x3, that's equal to 0. Right? And then we can complete our abstraction of this problem by going to the augmented matrix, right? But again, going from this physical chemical reaction, right? And then over here we have our nice linear system, right? Let's write down the augmented system, and then I'll make an important comment about this. So we have 3, 0, negative 2, 0, 0. Then we will have 0, 1, 0, negative 1, 0, and 1, negative 3, 0, 0. Let me put my zeros in there and there, right? So that's our augmented system. And notice that this system now has that additional property where all the B's are equal to 0. Do you remember what that type of system is called? It starts with the letter H, and this tells us that the system is homogeneous. And we know what's true about homogeneous systems. They always have at least one solution, right? In fact, if you end up with more variables than equations, which is what we have here, there are 3 variables, right? But only, there are 4 variables, but only 3 equations, then we know we're going to have infinitely many, right? Solutions. So what will that mean for our equation? Well, this is one application that I'm going to solve fully so you can see how that free variable is going to allow us to find a solution for x1, x2, x3, x4 that are all whole numbers, right? So let's see how it works. So the first thing that we want to do is to put this in one of our echelon forms. In fact, I'm going to take this all the way to RREF. So the first thing I'm going to do is multiply row 1 by 1/3. So I'm going to take 1/3 row 1, and that produces this system, 1 and then 0, negative 2/3, 0, and 0, right? And then the remaining 2 rows stay the same, right? So that's our first elementary operation. So we have our pivot there. Luckily, the way this system is set up, that we already have zeros beneath our first pivot. So next up, what we're going to do is eliminate. So I don't even have to really circle that the way I normally circle the pivots, but for sure, I'm going to have to use this term to eliminate the one below. So now using that as my pivot, I just need to take the negative of row 2 and add it to row 3. Right, so this means my first and second rows do not change. And then we'll have a new third row that ends up being 0, 0. This is equal to -3, and then 1, and then 0, right? So all I did was, again, I just took the negative of row 2, added it to row 3, and then this becomes the new row 3. So we're looking good, right? Next up, we have to make this a 1, right? If it's going to be an echelon form, I have to make this a 1. And then it will be in REF, but I think we should take it all the way to RREF just for more practice. And not only that, if it's in full RREF form, then we don't have to worry about back substitution, right? So at least we eliminate that step. That was a pretty bad pun, but anyway. Okay, so we got 0, 0, 1, -1/3, and then 0. All right. And this was almost in RREF as it is, right? The only difference is, the only problem is that this entry here, so here are our 3 pivots. And we have zeros below this one, we have zeros below and above, so that's good, but we have a non-zero entry here above this pivot. So, well, let's use that pivot to get rid of that non-zero entry. So here's our last operation that we need to do. If I take 2/3 times row 3 and add it to row 1, and let me write from the bottom up. So what are we going to get? We're going to have 0, 0, 1, -1/3, 0. And I'll close my brackets. Middle row is the same. 0, 1, 0, -1, 0. The first row changes slightly, and it's 1, 0, 0. So if I multiply this or actually this by 2/3, that gives me -2/9, and then adding it to 0 gives me -2/9 there, and then 0, right? So that's the system now in RREF. It just feels so, far removed from where we started in terms of this chemical equation. But don't worry, we're going to close the loop here. So the thing to notice, again, in fact, let me write it down. Our number of variables is 4. Number of equations is 3. So if you have a system in an echelon form with no contradictions, and you have more variables than equations, then you have to have at least one free variable, right? So what this tells us is we have one free variable. How do we identify it? Well, it is the variable that corresponds to the non-pivot column. So we had a pivot here, a pivot, there's a pivot here, there's a pivot there. There's no pivot, right? No leading entry in the 4th column. So that means my 4th variable is the one that I'll use as my free variable. So let's go ahead and do that. So let x4 be any real number. And now the bottom equation tells me that 1x3 minus 1/3 t is equal to 0. So just move that over and you've isolated x3. So x3 is 1/3 t. And then x2, and then this equation tells me that x2 minus t is equal to 0. So therefore x2 is whatever t is, right? And then finally the top equation tells me that x1 minus 2/9 t is equal to 0. So then x1 is 2/9 t. So let's write down our parametric solution set. In other words, let's write down all the solutions to this system. They have to be of this form: 2/9 t, t, 1/3 t, and then again t, where again t can be any real number, right? And that's fine. Any real number, you know, that I choose for t and plug it into this ordered quadruple, it will satisfy those three original equations. But we want our solutions to be a little bit more. Remember what we said, we want x1, x2, x3, x4 to be whole numbers, right? And in the application of chemistry, not only do we want them to be whole numbers, but we want them to have like no common factors. So it's like we want the chemical equation to be expressed in its lowest terms with reduced coefficients, right? So the question is, how can I get, based on the formulas that I see here, what value of t produces, right, whole numbers for x1, x2, x3, and x4, and let's add this other condition with no common factors. So with no common factors. Well, the clever thing to do is, if I want, for instance, when I look at this, if I want x1 through x4 to be whole numbers, then I would have to choose a t that's a multiple of 9, because then this would become a whole number, and these would naturally be a whole number, and then this would also be a whole number, because if it's a multiple of 9, then it automatically is a multiple of 3, because 9 is a multiple of 3, right? So putting that all together, we should choose t to be essentially the smallest positive multiple of 9, which would be 9, right? So that's our question there, and the answer is t equals 9. So if I choose t equals 9, let's write down what my values will be. So when t is equal to 9, x1 is 2/9 times 9, which is 2. x2 is going to be 9. x3 is 1/3 times 9, which is 3. And then finally x4 is 9. So now, notice we have our numbers, we have our coefficients, they're all whole numbers, and they don't have any common factors. So here is our balanced equation. So the balanced chemical equation is, drum roll, let's write it down. So it's going to be 2Al3 plus 9CuO, and then there's a reaction in the presence of heat, and then it's going to produce 3Al2O3 and then plus 9 CU, right? And we can always check. Now let's see. So let's do our little check. It's always good to have this check. On this side, let's check the ALs. So on the left we have 2 times 3, that's 6. On the right we have 3 times 2, which is also 6. Let's check the CU. So on the left, and the left side, that's where you have your reactants or your reagents, and then over here you have your product. So let's look at the, for Cu, well, we just have 9 there. And then on the right hand side, we also have 9 there. And then finally, let's look at the oxygen. So on the left, we have 9. And on the right, we have 3 times 3. That gives us 9. So that's it. Our chemical equation is completely balanced with whole number coefficients that have no common factors. So again, I hope that you are appreciating the scope, the breadth of applications that are related to linear systems. And believe it or not, we're just barely scratching the surface. Like everywhere you look nowadays in research, you see in all different aspects of study, you see linear systems popping up. So now you are familiar with some of those applications. So go forth and apply. See you soon.